Hello, and welcome to part 2 of developing your engineering intuition of structures. And today we're going to be covering the mantra of stiffer members attract more load. What do I mean by stiffer members? Well, a stiff member usually is one that's just thicker, bigger, heftier, deeper, longer. No, not longer. Um, with okay, well, for in the case of an axial rod, a stiffer member is one that has a larger cross-sectional area, and for a beam, a stiffer member is a beam that has a greater depth. So I'm going to go through a couple of examples. The first example is basically just simple two rods in parallel hanging from a ceiling fixed at the top, and then there's a unit load applied right in the middle. We're going to pull down on that and see how the load gets transmitted through those two members. And I have a couple different cases where in the first case both rods have the same area. In the second case, this rod has a little bit more area, so it's a little chunkier, and then the last case we got a really thick one. Now let's test it out. Run my model and see what happens. Alright, now let's visualize our axial force. And in the first case, we can see we pretty much split the load between the two rods 50-50. Makes sense. In the second case, though, check it out. Only about 0.375 of the unit load, that one kip, is getting split into the left member, but a lot of it, almost over double of what the left one is carrying, it gets split into the right member. So that load really, really likes this stiff member much more than this skinny one. And then in the last one, oh my gosh, when the load sees that there's this huge honking member right here, it's like, I'm going for this one. So it just kind of makes a mad dash. Now, you can kind of see that pretty much the proportionality kind of depends on, how big this member is compared to this one. So if you have a really skinny one, it'll pretty much take absolutely nothing, and the stiff one will do all the work. Poor stiff members, sometimes, I don't know. Alright, so the next example is pretty much very similar to the rods, but in this case we're just going to look at beams. So in this case we have, two same size skinny beams, and then we got progressively increase the size of our beams on the right in these two last cases. So there's a point load in the middle, and we're going to see how that load gets to the supports, because it can go through one of two paths pretty much. It can go through this beam and get to the left support, or go through the right beam and get to this support. Same thing with the rods. It could go through two different passageways. But how does the load decide which way to go? Well, again, it's the stiffer member that attracts most of the load. So let's check out the moment. So in this case, the moment pretty much gets split 50-50 into each beam, so the load is pretty much transferring into each member equally. But in these cases, you can see it's the stiffer members that attract most of the moment and most of the load from that point load. So the stiffer members attract the load. Pretty simple. You getting the idea? Hopefully. Now in the last case, it's pretty much just a combo between an axial rod connected to the ceiling, and then, just our nice little beam coming in here. Now, I'm sorry to say beams aren't very good stiff members. It's just kind of a pity. It's just these rods, they just kind of win out every day. I don't know. You'll see that mostly the rod is going to carry most of the load. But even in the case of a really thick beam, it's still not going to carry that much, just because beams are pretty flimsy. It's the rods. It's the rods you want. Now, let's check it out. First I'm going to look at axial force. So again, I have a unit load right at this point, and 0.91-ish of that load is getting transferred to my axial rod. So not a whole lot is going through my beam at all. It's a damn shame. No, well, in this case though, the beam is doing a little bit. The axial rod is taking maybe 0.7-ish, but still it's carrying most of the load. And in this case, the rod's pretty much doing everything. And you can double check that by looking at the moment. You can see there's not a whole lot of moment. There's a little bit more in this case, but it has absolutely nothing here. Now there's another good way of checking out how the load is getting distributed. through the beams, because remember how I said that the load can go through two different paths. It can go pretty much to the left one or to the right one. Left one or right one. It can go through the beam or go through the rod. And we can see if it's a unit load, then, in this case, these two cases, it's getting split 50-50 because the beams and the rods are equal. But not all beams and rods are made equal. Not all members are created equal. This one's taking 92% of that unit load. So rods are the way to go. Yeah. If you have an erection and you want to keep your a building erection, if you want to keep your erection standing, it's the rods that'll keep you up. Now, similarly, the same thing, you get different distributions, and it's the stiffer members that carry most of the load right at the support. So you can see most of the load is going to the support through the member that's stiffer. Alright, so hopefully that makes sense. Now let's check out our final, more complex example, and in this one, we're going to look at pretty much, imagine this being a cutout of our bridge, where we pretty much have our overtruss system here, and then we have our girders here. And applied to our girders, we have a distributed load, which kind of looks like this, right there. And it's going to be applied to the central girder, and what we want to know is where is this load going to go? Is it going to go to these supports at the girders, or is it going to go up through our tendons into our overtruss and go to these supports? And my prediction is it's going to go through the overtruss, because remember, the rods are stiffer, and that means they'll attract more of the load. The girders are just going to flop around and do stupid stuff and not really do a whole lot, but you need the girders, because you got to distribute those loads up into your overtruss somehow. Somebody's got to do it. It's a dirty job, but let's double check that. So now let's visualize, I guess, our joint loads to see where our actual load is being carried. And check it out. So at these supports connecting to the overtruss, we have maybe something like 11 kips of the overall load getting transferred here, but look at this load is going down, so really this collection of supports is only carrying half a kip here, so it's only about a kip that's going to the supports of the girders, and the other 11 kips, pretty much the majority of the load, is going through the overtruss. So the girders, they don't carry a whole lot of load. They're just serving the purpose of distributing the load up into your overtruss, and then your overtruss carries most of the heavy-duty loads. Alright, so let's check out some of the axial force diagram just for the sake of completion. And yeah, you can see a lot of the force is just going straight up into your overtruss and then going into your supports here, whereas the girders are just not doing a whole lot. Oh well. But that's okay, because, you just kind of design your girders so that they don't have too much, weight associated with them, just enough to kind of do their purpose. Now, why are these members not carrying any load? You're like, what the heck? What's going on here? Now, this is a topic that we will cover in the next lesson, if you are so keen to stay around, but I'll leave you with a cliffhanger for that one. Until next time. Alright, I'll see you guys later.